Hey everyone, well, welcome back to Probability Theory. This will be lecture 19 of the course. And in this section, we are going to discuss the last of our discrete probability distributions, and that is the Poisson distribution. So let's go ahead and jump into it. And we'll call this section 2.8, the Poisson distribution. And so let's go ahead and kind of set this up by sort of thinking through an example. Let's so consider the problem. All right, so let's say we want to identify the number of auto accidents at an intersection during a specific period of time, like maybe a week or something. So we wish to identify the count of accidents over a specific interval of time, right? And at an intersection, at a very specific intersection. Okay. So one of the ways to approach this problem is to say, well, let's take the entire interval of time and let's break it up into sub-intervals, right? And we'll just keep it general, and we'll say we break it up into n sub-intervals. Okay, and so a key point to make here is that these intervals have to be small enough so that only a single accident could occur within it, right? So assume these intervals are small enough that only a single accident can occur within one. Okay, so that's important. Right, and so that being the case, now let's talk about what the probability is. So let's say that the probability of one accident in a subinterval, let's set that equal to p, and let's say that the probability of no accidents in a subinterval is equal to 1 minus p, and then of course the probability of more than one in a subinterval, that's equal to 0. And that's because we've set the interval so small that this just can't happen. Okay. So given this kind of a setup, right, so you could potentially have an accident here, you could have one here, potentially one here, you've got some range, some total length. So given the setup, you can kind of see that the total number of accidents that occur over this entire period is really just the sum of the subintervals that contain an accident, right? So the total number of accidents is just the sum. It's the sum of the intervals that have an accident in them. Okay, so you can kind of see how that's the case. And that being what it is, then I mean you can kind of think of this as a binomial distribution, right? As long as the intervals are sufficiently small and they are all independent and they all have identical probability, then you can really think of this as a binomial distribution. So this looks like a binomial distribution. Okay. All right, remember the binomial distribution, a random variable that has a binomial distribution, is basically counting the number of occurrences that will the number of successes, in a range of occurrences, in n occurrences or n trials. How many successes did you get? And so here we have n intervals, and we're interested in how many of them have an accident, right? So you can kind of think of this as a binomial distribution. Okay, now let's see what happens when we let so really what makes this not a binomial distribution is this interval concept, right? You've got these discrete intervals here, right? So let's see what happens when we shrink these intervals down so that they're basically let them go to 0 in terms of the width of the interval, which is another way of saying that we let the count of the intervals go to infinity, right? So basically what we're saying is let's see what happens. Let's let the size of the intervals go to 0, and the count, therefore, go to infinity, right? And so we're specifically, remember, interested in the probability distribution here, and so what we're going to do is we're going to use the binomial distribution to start with. So we're going to let the limit as n goes to infinity of n choose y times the probability of y times the probability of 1 times 1 minus p to the n minus y. Right, so the limit as n goes to infinity of n choose y, p to the y power times 1 minus p to the n minus y. And so remember, this is the binomial distribution. N is the total number of trials. We're going to let that go to infinity. And y is the specific value of the random variable that we're interested in identifying the probability of. And so we're going to see what happens when we take this limit. Okay, and so let's just extend this a little bit. So we've got the limit as n goes to infinity. Now I'm just going to write this out. So I've got n minus 1, dot, 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 all the way down to 2, down to 1. And in the bottom I've got, what do I have in the bottom? n minus 1. Oh, sorry. So I've got n minus y factorial down below and y factorial. Okay, and that's all times p to the y times 1 minus p to the n minus y. Now, obviously, you're going to get the cancellation here. And so what does that all look like? Well, you've got basically the y factorial, sorry, the n minus y factorial is going to cancel out a whole range of this, right? So you're going to have n minus 1, dot, 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 all the way down to n minus y plus 1, right? And that's going to cancel away that one and all of these smaller ones. And then below that, we're still going to have the y factorial. And then over here, I've got p to the y, 1 minus p to the n minus y still, right? Now, what we want to do next is we're going to introduce basically what will become the parameter for a Poisson distribution. So we're going to introduce lambda, and it's going to be, we're going to set that equal to n times p, which of course means that p is equal to lambda over n. So this is lambda, right, which is a Greek character. Okay, right, so we've got this new value that we're introducing here. Okay, so let's substitute that in. Okay, so we've got the limit as n goes to infinity of n times n minus 1, dot, 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 n minus y plus 1, all over y factorial. Now, instead of p, I'm going to write lambda over n, and that's still going to be to the y power, and then 1 minus lambda over n to the n minus y power. Oop. Okay, so I've still got this, right? So all I did was basically sub in for these guys here. Okay, and we're going to continue to do a little bit of algebra on this. So the limit as n goes to infinity. Okay, so I'm going to do a little bit of rearranging here. And I'm just going to bring the lambda to the y power, and I'm going to put that over the y factorial, right? So I've got lambda to the y over y factorial. I'm going to kind of keep those up front here. And then I've got 1 minus lambda over n, which I'm going to put here. Okay, and then the rest of it I'm going to have here, because remember, when you multiply these, you add the exponent. So I've also got 1 minus lambda over n to the negative y power. Okay, and then I got to hang on to all of these terms here. So I've got n times n minus 1, dot, 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 times n minus y plus 1, right? And then the thing that that's still outstanding here is the n to the y power. So I'm going to put that under here. Okay, I'm just all I've done here is reshuffle some things and pull some things apart. Sorry, that should be to the nth power there, right? So I've just kind of rearranged some things and shuffled some stuff around. Okay, and what's the point of doing that? Well, I can factor some stuff out. So this is a limit for, as n goes to infinity. So these two we're stuck with these. They're going to come out front. So I've got lambda to the y power over y factorial times the limit as n goes to infinity. And basically what I have now then is 1 minus lambda over n to the nth power. times 1 minus lambda over n to the negative y power. And now this whole thing we can do something nice with. And what can we do there? Well, this is really just equal to 1 minus 1 over n times 1 minus 2 over n dot 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 times 1 minus y minus 1 over n. Now, where did this come from? Well, all we're doing there, if you think about it, is we're just kind of doing a little bit of algebra here. So in particular, what have I done? 1 minus 1 over n times 1 minus 2 over n dot 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 1 minus y minus 1 over n. Well, you can just, kind of get a common denominator in each of these, and you've got n minus 1 over n times n minus 2 over n dot 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 times n minus y plus 1 over n, right? That's this one. Right, now this, right, how many n's do I have? Well, I've got y of them, right? 1, 2, all the way up to y plus, so my n minus 1 all the way up to n minus y plus 1, so that's n of them. So this is just equal to n minus 1 times n minus 2 dot 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 n minus y plus 1 all over n to the y. And so that's just all I've done there. Okay, that's what this piece here is. Okay. All right. And so on the next page, right, so what do we end up with? We had so lambda to the y over y factorial times the limit as n approaches infinity of 1 minus lambda over n to the nth power times 1 minus lambda over n to the y power times 1 minus 1 over n times 1 minus 2 over n dot 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 times 1 minus y minus 1 over n. Okay, so now notice that note that the limit as n goes to infinity of 1 minus lambda over n to the nth power, this is equal to e to the negative lambda. Now that's something that you may have to spend a moment trying to understand. Where does that come from? But this is something you will have seen, I believe, in calculus 2, although we didn't use lambda then, but I do think we looked at this one. And so that being the case, and then also the fact that all of these go to 1, right, in the limit, those all go to 1, right? If you let this go to infinity, then this is just 1 minus basically 0. 1 minus 0, 1 minus 0, so those all go to 1 in the limit. And so what we end up with here is lambda to the y power divided by y factorial times, so basically this goes to 0, this goes to 1 as well, right? That goes to 1. This one, that should be negative. This one is the only one that we keep, and that is equal to e to the negative lambda. Okay, and so this is the form of the probability distribution for a random variable y that has a Poisson distribution. Okay, so this is the probability distribution for a Poisson random variable. Okay, now remember what these things are. Lambda is a constant, y is the variable, and e is a constant also. E is the transcendental number 2.718 something or other. Right, it's kind of like pi, but it's e. So the Poisson distribution, the Poisson probability distribution, is a good model for the number, we'll say y, where y is the number of rare events that occur in some measure. So y is the number of, and we'll say rare events, like auto accidents in an intersection, that occurs in space or time, right, or something like that, some or other measure, right? So that's the Poisson distribution, similar to the binomial distribution, but in this case we let n go to infinity of the binomial distribution, and this is what we get. So formally, well, let's define it here. A random variable y is said to have a Poisson probability distribution if and only if the probability of y is equal to lambda to the y power divided by y factorial times e to the negative lambda. And this is going to be for y equals 0, 1, 2, and on and on. And in this case, lambda has to be greater than 0. Okay. Now this lambda is said to be you could think of lambda as the parameter of the Poisson distribution. It really is the average value of y. Right. So for example, with an auto accident at the intersection, maybe your average number of accidents per month is 10 or 5. Then you would set lambda to equal to that value. Okay, and let's do that example. Let's work on that example that we started with. So let's say a traffic intersection averages 2 accidents per month. An intersection averages 2 accidents per month. Okay, what's the probability of 3 accidents in a single month? Okay, so given what you know about the number of accidents per month, the average is 2. What's the probability that next month there'll be 3 accidents? Okay, assuming nothing changes. Right, so you can think about this problem. You think about all of the conditions, right? So first of all, the accidents are all going to be independent, presumably, right? And the probability of an accident is always the same, right? So independent accidents always, the probability is p, right? So the probability doesn't change from minute to minute at this intersection, presumably. It's an assumption. We have an average number, so lambda is equal to np, which is equal to 2, right, per month. That's constant. Right, so that's part of this one here. Probability is equal to p, right? So the probability is constant. The average we'll assume is constant. So that's satisfied. And then, of course, we assume that 2 accidents cannot occur at the exact same time, right? So that's fine. In theory, if the size of the interval is 0, then you obviously can't have 2 accidents at the same time. 2 accidents cannot occur at the same time, right? And so these are really the 3 things you have to check in order for this to be a Poisson random variable. And so let's take a look at what we think that probability is. So we would say that y is the number of accidents in a month. All right, and in this case, we would say that y is a Poisson random variable with parameter lambda, where lambda is the average number of accidents in a month, and lambda is equal to 2. Okay, and so what we want to know is what's the probability that there are 3 accidents in a month. Right, so the probability that y is equal to 3 is just probability of 3. And remember, the probability of y is equal to lambda to the y power over y factorial times e to the negative lambda. All right, so this is our probability distribution for this guy. And so our probability, in this case, lambda is equal to 2, so there'd be 2 to the 3rd power divided by 3 factorial times e to the negative 2. Negative lambda, so lambda is 2. Okay. And so when you do all that math, you just kind of crunch this through with a calculator, you should get 0.18. So there's about an 18% chance of 3 accidents in a month. Approximately an 18% chance of 3 accidents next month. Okay, so this is a very, I mean, you can just imagine how useful this kind of a distribution could be, right? So anytime you've got an interval of time or space, and you know the average value, the average count of an occurrence, then this can be used to generate probabilities all around that average, right? So the probability of 3, what's the probability of 4 or less, what's the probability of 0, etc. Right? And it's a very simple problem statement, and the Poisson distribution is a very kind of powerful way to think about this or to solve these problems. What about, for example, let's find the probability of more than 2 accidents in a month. Right, so we want the probability that y is greater than 2. Well, that's equal to 1 minus the probability that y is less than or equal to 2, right? Which we know is just 1 minus the probability of 0 minus probability of 1 minus probability of 2, right? And so we can calculate each of these, right? We're just going to be using the same distribution, just different values of y. So we've got 1 minus 2 to the, remember lambda is 2, right? And so lambda to the y over y factorial times e to the negative lambda. So 1 minus 2 to the 0 power over 0 factorial times e to the negative 2 minus 2 to the first power over 1 factorial times e to the negative 2 minus, so we got those two. Now the third one is 2 to the second power over 2 factorial times e to the negative 2. Right? So that one. Okay, so this is the probability of 0. This is the probability of 1. That's the probability of 2. Right, these whole things. Right, and so you just calculate each of those individually. Right, you can do a lot of simplification here. So this is really 1 minus, this is all just 1 times e to the negative 2 power. And then this one, you get 2 times e to the negative 2 power. And then this one, you get 2 times 2 is 4 over 2. And so that one you should get, again, minus 2e to the negative 2. And so this whole thing is 1 minus 5e to the negative 2 power. Okay. And you can plug that into a calculator and you'll get 0.32. So there's about a 32% chance of more than 2 accidents at this particular intersection in any given month. Okay, very cool. So this has been an example of using the Poisson distribution to describe the number of events occurring over an interval of time. What about using the Poisson distribution over an interval of space? And this next example kind of addresses that. So this is taken from the textbook. A certain type of tree has randomly dispersed seedlings. So a tree has randomly dispersed seedlings with approximately 5 seedlings per square yard. Right? 5 seedlings per square yard. If we were to identify a random 10 square yard area, so we identify a random 10 square yard area, what's the probability that so 1 square yard regions inside will have seedlings? So what's the probability that 1 square yard, sorry, what's the probability that none of these have seedlings? Okay, all right, so let's think this through. So I've got some area, right? And we'll say this is 10 square yards, right? And it's broken up into these sub areas, and it doesn't have to necessarily be contiguous like this, but you know. And then according to the data that I have, I'm able to approximate that 5 seedlings per square yard, right? There's approximately 5 seedlings per square yard. So I identify a 10 square yard area, and I ask, what's the probability that none of these have any seedlings? Not just 5 or less than 5, but literally none for this entire 10-yard plot. Right, and we can think about this from the standpoint of just a single square yard. There's different ways to do this, and we'll do it in a different way in a second here, but let's think about this from the standpoint of just a single square yard. From the standpoint of a single square yard, we would say that y, being the number of seedlings, is Poisson distributed with lambda equal to 5. So on any square yard, we would expect to find 5 seedlings. So the question is, what's the probability of none? And I should say, sorry, what's the probability of no seedlings on a single square yard? I should be careful here. Right, so basically I want to know the probability that y is equal to 0. Okay, and so we know that this is a Poisson random variable, so this is just going to be 5 to the, so it's lambda to the y power over y factorial, so 5 is our lambda, y is 0, and so then it's 0 over 0 factorial, and then it's e to the negative lambda, so negative 5. Okay, and so this would be 1 times e to the negative 5, so it's just e to the negative 5. Okay, and so the probability of no seedling on a single square yard is e to the negative 5. Okay, so the probability of no seedling on a single square yard is e to the negative 5 power, whatever that happens to be. And so we can kind of blow this up because these square yards are all random and independent, presumably. We can blow this up by just multiplying this out. So the probability of no seedling on 10 square yards is e to the negative 5, right? But this is just to the 10th power, right? So 10 of these. So e to the negative 50th power. Sorry about that. Okay. So that's kind of the first approach. I mean, you can just say, well, it's really a question about 10 square yards, but I've got, my lambda is defined for just a single square yard. Well, another approach would be to adjust the parameter lambda to reflect the 10 square yard area, right? And let's see what happens then. All right, so let's let x be the random variable, the number of seedlings on a 10 square yard area. Okay, then x would be Poisson with lambda equal to, so think about this, if I expect 5 seedlings per square yard, then I should expect 50 seedlings per every 10 square yard. So lambda in this case would be 50. Right? And so then the probability that x is equal to 0 is just 50 to the 0 power over 0 factorial times e to the negative lambda, which is e to the negative 50 power. And of course, you get the same answer as before. Okay. Very good. Let's do one more example. This will be another time example. So a tech support help desk receives emails at an average rate of 3 per hour. A help desk receives emails at an average of 3 per hour. So let x be the number of emails that will arrive in the next hour. What's the probability that x is equal to 5? So what's the probability of 5 emails in the next hour? All right, so let's define the random variable. X is equal to the number of emails in a given hour. And we would say x is Poisson distributed with lambda equal to 3. 3 is the average. And you get this lambda from data, right? You observe, well, what is our average? That's easy enough to calculate. I got 2 this hour, I got 3 the next hour, I got 4 the hour after that, then I got 3 again, and blah, blah, blah. And you kind of go through this and say, well, what's the average per hour? It's 3. And so you can set your lambda that way. And so the probability that x is equal to 5 emails in the next hour, is just equal to 3 to the 5th power, lambda to the y power, over y factorial, which is 5 factorial, times e to the negative lambda, which is e to the negative 3rd. Okay, and so you can calculate that, and you should get something like 0.1008. Right? And you could do any number of variations. So what's the probability that no more than 2 will arrive? What about that one? Yeah, so the probability no more than 2. Well, that's the probability that x is less than or equal to 2, right? And so that's just the probability that x is equal to 0 plus the probability of 1 plus the probability of 2. Okay, and you can easily sort this out, right? This is going to be 3 to the 0 power over 0 factorial times e to the negative 3 plus 3 to the 1st power over 1 factorial times e to the negative 3 plus 3 to the 2nd power over 2 factorial times e to the negative 3. Right? So these all kind of have the same structure. Only thing that's varying is the y, right? So you can see that. And so when you do this, you would get like what? E to the negative 3 power plus this would be 3 times e to the negative 3 plus, and this will be 3 times 3 is 9 over 2, 9 halves e to the negative 3, right? And you can simplify that. Or convert that to a decimal as you see fit. Okay, so that's the Poisson distribution and a bunch of examples. Let's talk about the mean and the variance here. Okay, so theorem. If y is a Poisson random variable, with parameter lambda, then the mean of y, the mean of this distribution, also known as the expected value of y, is equal to lambda. And the variance is equal to lambda as well. Okay, very nice. Those are the kinds of means and variances we like to see, where they just equal the parameter. Isn't that nice? Let's go ahead and take a look at the Let's go ahead and take a look at the mean here and prove that this is the case. This isn't too difficult of a proof. So we'll start by just defining what we mean by the expected value. In this case, this is equal to the sum over all the y's. Remember, y is from 0 to infinity, positive integers. So it's the sum over all the y's of y times the probability of y. Okay, and that's equal to the sum from y equals 0 up to infinity of lambda to the y power times e to the negative lambda over y factorial. And I forgot the y, so I'll put it back here. Usually I put the y on there, don't forget that. Now the first term is, in this case, is going to be 0, since this will be 0. So we can increment this up 1, and that's always helpful to do. So y equals 1 up to infinity of y times lambda to the y, e to the negative lambda over y factorial. Okay, so the first term is 0. Okay, and so that being the case, we can rewrite this. Okay, we can rewrite this as sum from y equals 1 up to infinity of lambda to the y, e to the negative lambda over y minus 1 factorial. Okay? Right, because you can cancel here, right? Cancel the front, cancel this y with the front. Now you just have y minus 1 down there. And then let's factor out the lambda, because lambda is not, factor out one of the lambdas. Right, what we're trying to do is kind of get the y up here to be y minus 1, so we can factor one of the lambdas out. And so we do that, and we get lambda to the y minus 1 times e to the negative lambda over y minus 1 factorial. Okay, and then let's just do a change of variable here. Let's let z equal y minus 1. Then what do I get? I get lambda times the sum from z equals 0 to infinity of lambda to the z times e to the negative lambda all over z factorial. Okay, and then of course this thing here, this is the probability distribution for a random variable z that is Poisson lambda. Right, and so we know that specifically this sum is equal to 1. Right, so this whole thing is just equal to lambda times 1, which is lambda. Right, and so that's what we're trying to prove, that the expected value of y is equal to lambda. And you can do something similar, similar kinds of moves for the variance. I'll let you work on that one. Okay, and so I think that's where we want to stop with this section. And so that was the last of our discrete probability distributions. Next up, we'll talk about moments and moment generating functions. So we're getting very close to the end of the discrete probability section, and then we'll be moving to continuous. But we've got a few more topics to cover. All right. Until then, take care. We'll see you next time.